Hey guys, Jason here from Timberfalls, home for CNC creators like you. One of the most important topics that seems like is misunderstood is chip load, feed rate, step over, step down, and how all of that relates. The first thing I wanted to talk about was the database that is inside of Carveco. This database is very similar to the one that's in Vectric. All of these databases come either from the software company or you can download the different databases from the manufacturers. Now, the thing that I want you to note is that all of these settings or bits in these different libraries are very generic settings. And the reason these are generic is because they're not machine specific. So if you think about this, a hobby style desktop CNC is not going to cut the same as a mid-range hobby CNC, which is also not going to cut the same as a small commercial CNC. So all of these different machines have varying degrees of rigidity, the horsepower of the spindle that they're using, and the capabilities of the machine itself. So given all of these different things, there's no way that one setting for a bit would work the same with all of those machines. So it doesn't make sense to think that the settings in this software are going to be optimal for every single bit, for every single machine. These settings are placeholders for entering the correct information for your setup. And I think that's part of the thing that so many people miss with chip load and with bit settings. They buy a machine, they buy some bits, they look at what the manufacturer says, they look at what the software says, and sometimes there's a variance between what the manufacturer says and what the software says, and the manufacturer's lists are also not machine specific. So the best way to think about this, and what I want to do is I'm going to open up a chip load chart. Now, the chip load chart that I have opened up is a web-based chip load chart. If you guys were to go to Google and just Google chip load, you probably would get a chip load chart with very similar settings and numbers. Now, to understand what chip load is simply the size of chip per flute. So every flute on a bit, let's say we have a 2-flute end mill, every time that bit makes one revolution, we're going to cut 2 chips. That's because there's 2 flutes. So chip load is the chip size per revolution per tooth. Now, the size of this chip is important because it carries heat from your cut out of the cut. So when you're cutting material, heat is generated between the bit and the material, a lot of heat. Now, in a perfect situation, 80% of this heat is carried away by these chips. So if your chip is too small, the heat carrying capacity of that chip will be very limited. And if the chip is too large, then the density of that chip will also create a situation where the heat cannot penetrate it, and the heat carrying capacity of that chip is diminished. When 80% of the heat is being carried away by the chip in the perfect situation, when it's not being carried away, that heat remains in the material and it remains in the bit and collet. So what happens is when you have excessive heat remaining in your project or in your wood, as you start cutting a project from one side of the material over to the other side, usually with a raster tool path, you're removing material across the side, and as this heat is being generated, it's going to penetrate the wood, and then as the wood cools, it will start to cause bowing and flexing. And so if you notice that you have a lot of wood bowing or warpage after your cuts, this is because a lot of excessive heat is staying in the material and the bit. Now, the other side of this is where the heat remains in the bit, the bit gets hot, and when the metal gets hot, it starts to temper. And when metal tempers, it becomes brittle, and that brittleness is what makes the sharp edge of the flutes become dull. So two compounding factors happen. Your wood has a lot of heat and warpage, and then your bit becomes dull. That dull creates chip out. Your projects will not be as clean. So by having an optimal chip load, you will have a better cut in your projects. You will have less warpage, and your bits will last longer. So to understand chip load, we have to understand that all wood or all pieces of material have a different density. Okay, and density is how thick or how hard that wood is. Now, on one end of the spectrum, we have particle wood, MDF, pine. Those are all materials that are extremely soft. In the middle, we have plywood, and the reason that we put plywood in the middle is because plywood is sometimes a mixture of soft and hard woods. And because the makeup of that plywood is a combination of these two, it sort of runs in the middle of between soft, middle, and then what you call hardwood. And then we have hardwoods, which is everything in the hardwood species. Now, each one of these three categories has a range. So we have the softest of softwoods to the sort of, harder of softwoods. We have our range of plywood, and then we also have a range of hardwood. Hardwood, you may have like really soft maple is an example of soft hardwood. Hard hardwoods would be something like ironwood or ebony. I mean, these woods are extremely dense and extremely hard. So we have a variance, and that's what's important to know, is that chip load is a variance between the hardness of the material and the size of the chip that you need to cut out of that material in order for it to have good heat carrying capacity. Now, the lighter and softer the material, the larger the chip needs to be to have good heat carrying capacity because it's less dense. On the other end, the harder the material, the less heat carrying capacity can happen in a dense chip, and so those chips are smaller. And that size of chip is what is represented in the ranges of these chip loads or chip load chart. Now, this particular chip load and the chip load that you will find online on all your chip load charts is essentially what the industrial standards are. Industrial standards are what the biggest machines out there are using to calculate the proper chip load for the type of material that they're cutting. And this takes away the rigidity and the horsepower of the spindle, because those things at this point are not the weak part of your operation. The bit is now the weakest part of our operation. But if you look at these charts, and I'm just going to select a 1/4 inch, and we're going to look at hardwoods. And if you go with industrial standards, which is a chip of 0.009 to a range of 0.011, and then the chip load chart wants how many revolutions we're spinning per minute. So we're going to enter in 18,000. The next thing we'd want to do is enter our flute count and an average 2 flute end mill you cut wood with. And then if we take a look at this chart, we can instantly see that it is calling for a feed rate of 324 to 396 inch per minute. Now, the thing to know is that most hobby style CNC all hobby style CNC machines cannot produce this feed rate because of the two limiting factors, which is machine rigidity and spindle horsepower. So in hobby style machines, this is the limiting factor, not the bit. Industrial standards, they're using the same router bits or CNC router bits that you are. So in hobby CNC, the bit is not the limiting factor. It is the machine and it is the spindle horsepower, because in a perfect situation, 324 inches a minute to 396 inches a minute is the proper feed rate. So because of that, that's why this is really complicated for a lot of people, because they want to try to figure out exactly what the right number for their machine is. So what we have to do is to start to lower some of these chip load numbers, and we also reduce our depth of cut, because this chip load chart is rated at the diameter of the tool, and it says right up here at the very top that this, or maybe it says right here, equal to the tool diameter. Depth of cut is equal to the tool diameter. And then if you want to factor in, let's say you wanted to go 2 times that tool diameter. You got a 1/4 inch end mill, you want to use it a 1/2 inch cut deep, then you would add 20 to 25% to these chip load numbers. For hobby CNC, we're going to do just the opposite. We're going to reduce the 20 to 25% to get down into a chip load range that our machines are capable of. And the first thing I'm going to do, let's go back to that 18,000 RPM, and we would reduce this down by, say, 20 to 25%. And what the number that I've figured it out is, it's really 0.002. And this is sort of where the high-end hobby style CNC machines will begin, at about 0.002, less than this chip load. The further down the hobby CNC range, where you get into your sort of your mid-range hobby CNCs and then your desktop hobby CNCs, you're going to want to reduce this by 0.003 or maybe even 0.004. Now, that is how you would calculate using the chip load chart. Now, having said all of that stuff, I want to give you guys a very simple and easy way to actually figure out what the optimal chip load is for your setup that doesn't involve any of this stuff. These numbers, the concept behind this is to remove heat from the material and the bit. And that's the 2 important factors. So the cooler that your bit and the cooler that your material is, the better your chip load is. So the best way to test chip load is to test bit temperature. And I recommend buying one of those cheap $12, $14. They have these little infrared test heat guns that are thermometers. If you get one of those, you let the cut start a few minutes in, you pause the router, pause the cut, and you take a temperature of that bit, and you want to find out what the temperature is. Then you're going to want to make an adjustment to either your feed rate or your RPMs, and you want to test that temperature again. If the temperature went down, then you are going the right direction. If the temperature went up, you're going the wrong direction. Now, in layman's terms, if you can reach up and touch the bit with your hand, it is cool enough to touch with your hand, then you are getting to an optimal chip load. If that bit is too hot to touch, if you reach up and you feel heat coming off of it and you barely touch it and it feels like it's going to burn you, then your chip load is very off. And the difference between having a good chip load and a bad chip load is the difference between having less chip out, cleaner cuts, longer lasting bits. So this is a great thing that beginners, when you first start out and you first get a machine, the first thing you could do is to test what type of wood you're cutting and what the best settings for that cut is. And you're simply just looking for the coolest bit temperatures. And that essentially will give you the best chip load. And it's sort of the easiest way to think about chip load in general, because your chips need to be the right size in order to carry that heat from your cut. And this is true in all materials. One thing to note is that there's a difference between downcut, upcut, and compression bits when it comes to chip load. A downcut bit is forcing the chips downwards towards the base of the bit. And so the base of the bit is actually recutting those chips at the bottom. An upcut bit is forcing the chips up and out of the project. And so because of that reason, an upcut bit can achieve a slightly higher feed rate downcut bit. So when it comes to speed, upcut, it will always produce a faster cut. Upcut leaves a clean bottom surface while pulling the fibers up and out. So it always leaves a frayed top edge. Your downcut bit will shear that top edge and force all of those chips downwards. But because they're recutting at the base of the bit, the base or the bottom of your cut will always have these marks or little swirls. Now, a compression bit has a small upcut portion at the bottom of the bit that's giving a clean surface bottom. It's forcing those chips up to the middle of the bit. And then the top of that bit is a downcut portion that forces and shears the chips so that they meet right in the middle of that bit. Now, the only downside to a compression bit is that sometimes where these chips compress in the middle of the bit, you can get some slight amount of marks on your sidewalls of a profile cut. And so you have disadvantages and advantages for all three types of bit: downcut, upcut, and compression. Now, a compression bit can run a little faster than a downcut bit because of the upcut portion pulling those chips off of the surface. But a downcut bit generally is your slowest of chip loads when it comes to chip loads and when you're testing chip load. So it's important to know that this is a part of the chip load test and getting the optimal settings. So an optimal setting for an upcut bit will be slightly different than the optimal setting for a downcut bit. That in regards to chip load. Now, the other way that we reduce chip load with a hobby style CNC machine is to use less step down. Step down, or depth of cut, is how deep each pass of the bit is going to be. And so typically in industrial standards, you would use the diameter of the bit. But with hobby style CNCs, it's better to use half the diameter of the bit. So if you're using a 1/4 inch bit, you would want to use a 1/8 inch step down. Now, the exception to this rule is in a compression bit, you have to have a step down that covers both the upcut portion and the downcut portion of the bit. If your step down is too shallow, then the downcut portion will not reach the top edge and you will get top fraying. Now, step over is the other setting that I talked about, and step over has really a lot to do with the quality of the cut more than it has to do with chip load. Step over does start affecting chip load just above 30% of the diameter of the bit. If you were to take a look at a end mill bit and measured the distance of the flutes from the outside edge to the inside edge, you would notice that there's a core or a central part that is not covered by a cutter. Now, when you get over 30% of the bit, you're starting to crowd the center of the bit. Now, when you're clearing, a lot of people will use 40%. I've even seen some people use 50%. And while this will clear faster, do know that in a hobby style CNC machine that there are pressures that are affecting chip load after about 30%. So when we're clearing or we're just removing material, the finish and the quality is not important. But when you're doing a finishing pass, or when the surface or the quality of your cut matters, your step over should be really low, somewhere between 12 and 6%. A lot of people will say that 8% is the Goldilocks percentage, and that is true for some bits. The bigger the bit, the more effect step over will have on how much scalping happens. As that bit steps over, there's a portion that's not cut, and that portion is called a scalp. So every time you step over, you get a very, very small scalp. The bigger the bit is, the more that percentage is amplified, and so the bigger the scalps get. The smaller the bit, the less effect step over has, and so the less scalping you will get. And what I mean by that is, if you have a 1/8 ball nose, and let's say you're using 10% step over, you'll get significant scalping lines all the way across your Rasta toolpath. But then if you were to change and put in a 1/16 ball nose and run the same 10% of 1/16 is a lot less than 10% of 1/8. And so the scalping or the marks that has will be a lot smaller, even at the same percentage. So the smaller the bit, the less impact that the step over has on quality. But the larger the bit, the more impact step over has on the quality. And then when you get to like 30%, you start affecting chip load. So that's how step over affects both chip load and cut quality. I did not mention what plunge should be on a hobby style CNC machine. Generally, your plunge is half of whatever your feed rate is. So if you have a 100 inch per minute feed rate, you generally would like to have a 50 inch per minute plunge. The exception for this, I would say, is when you're doing 3D finishing passes with a taper ball nose bit. Taper ball nose bits have a really long cutting surface. They're designed to cut deep. And because a finishing pass in 3D, the wood left over from the roughing passes is very minimal. And so in this situation, you can run your plunge the same speed as your feed rate. So if you have a 120 inch a minute feed rate, you can run a 120 inch a minute plunge at the same time. And that's generally with the taper ball nose bits and finishing passes in 3D when you're cutting very little material. I would tell you most people run their machine too slow. That is the consensus for most hobby style CNC machines. They run their machine too slow, or they start to learn about chip load and they go way too fast, trying to think that you're going to maximize your machine to the top of its performance. But hopefully what we talked about today will save you guys a lot of heartache and save you some steps on getting your situation dialed in, or your machine dialed in. I'd like to give a big thanks to all of our Timberfalls Elite members. You guys keep the bit spinning, and we really appreciate your support. If you're interested in becoming a Timberfalls Elite, check out the link below or our website at timberfalls.us. Thanks, guys.